Welcome to a lesson with Dr. Powell. Let's take a look at what it means to add up an infinite number of things. Say, for instance, we had a 6 plus a 12th plus a 20th plus a 30th plus 1 over 42. Do you see a pattern? Well, add 6 here, add 8 there, add 10 there, add 12 there in the denominators. There is a pattern that continues indefinitely. Now, what does it mean to add all of them up? And how can this be defined? Well, if we take a look at just adding one thing up, maybe just to here in the sum, we'll call that S1. Just add one thing. Now, if we add two things, let's call that S2. 6 plus a 12th, and so forth. S3 being adding up to there would be a 6 plus a 12th plus a 20th, and so forth. Notice that out of this, so we've taken a list of things, 1 6, 1 12, 1 over 20, and so forth. Instead of having commas, we have pluses. If we had commas, that would be called a sequence. With pluses, it's called a series. So if we're adding up everything in a sequence, that's a series. So a series is with plus, and a sequence with comma. Okay, but notice that actually out of this series, we get another sequence, namely this one, S1, S2, S3. We're getting a sequence list right here. And these are called the partial sums. S1, S2, S3, S4, and so forth. Now, these partial sums form a sequence. The sum here of the series we define to actually be the limit of a sequence, the limit of the partial sum sequence. So what happens as we increasingly add up more and more and more and more and more and more and more things? So this limit, whatever that is. Well, if we could come up with a nice formula for S sub n, then we could take a limit of that as n goes to infinity, and we'd see the sum. Let's see how we might come up with a formula for this. First of all, well, we can do this in a couple different ways. So we'll begin as follows. Notice that 1/6 is the same as saying 1/2 minus a third, because you kind of think about if your common denominator, you're going to get a 6, and 1/3 is 1/6 away from 1/2. The next term in the sequence before we're added, so this is not the sequence of partial sums, this is the original sequence, 1 6, 1 12, and so forth. Notice that 1 over 12 is the same as 1 over 4, or 1 over 3, sorry. 1 over 3 minus a fourth, for the same basic reason. 1 over 20 is 1 over 4 minus a fifth, and we could keep going. But notice as we add, something interesting occurring. If we add the first two together, those cancel. If we add the first three, those cancel. And if we keep going in this manner, we'll notice that every time we only have two terms remaining. So when we have S sub 1, we have 1/2 minus a third. S sub 2, we have 1/2 minus a fourth. So the last one, the first and the last are always that are preserved. S3 is 1/2 minus a fifth, and so forth. Can you come up with a formula for S sub n? Do you see a pattern? We'll have a 1/2, and notice that this 3 is 2 more than the 1, the 4 is 2 more than the 2, the 5 is 2 more than the 3. So we have 1 over n plus 2. There's our formula for S sub n. Now, maybe you wouldn't have noticed, first of all, that 1/6 was 1/2 minus 1/3, 1/3 minus a fourth, and so forth. But maybe, perhaps, we could have seen that 1/6 is the same as 2 times 3, and 12 is 3 times 4, and 20 is 4 times 5. And maybe we could have thought, this looks an awfully lot like n times n plus 1, where n changes, n starts at 2. So our series, we could have thought as n times n plus 1, the 1, as n goes from 2 to infinity. Now, if we're familiar with partial sums, actually that's where we can get this. We could have thought, okay, this right here can be decomposed into something like this, with something on the top here and something on the top here, just in here. Okay, how do we get it? Well, we know that how we can cover up n. If we cover up n so we don't see it anymore and plug in 0 into the rest, that's because, well, 0 we don't want to plug in on this part, but let's plug it into everything else, and we'll notice a 1. That's what goes up here. Now, what goes over n plus 1? We cover up the n plus 1 now, and we plug in what would make this 0, which is -1, into the rest. 1 over -1, so we get a -1. Notice 1 over n minus 1 over n plus 1 would match exactly what we're having here, starting at 2. 2, 1/2 minus 1/3. So partial fraction decomposition can get us this, and then we can go forward here, find a pattern, and label precisely a formula for S sub n. Now we can take the limit of S sub n in order to find the sum. Do you see what it is as n goes to infinity? Well, this part right here goes to 0. So we end up just getting 1/2. So the sum of all of those is simply 1/2. And that's the way we can define a sum as we keep going in that manner. Thanks for watching.